George Romanic here. In today's video we are going to make a beautiful connection between atmospheric sciences and pure mathematics. Mathematics is a language of nature, of this universe, and it is very useful to know that language and to know how to use that tool. In my last video I derived an expression that describes how pressure changes with the altitude in an atmosphere in which temperature decreases exponentially with the height. I will show you this expression for pressure shortly, but you will remember that in the definition of this exponential decrease of temperature we had the scale parameter that dictates what is the rate of this exponential decrease. And I claimed that if this rate of exponential decrease is very slow, and that means that parameter, which we called k, goes to zero, the temperature profile should approach isothermal temperature profile, temperature constant with height, and therefore the pressure profile should approach simple exponential decrease with the altitude. Everything will be clear now. Let's go and see the beautiful interplay between pure mathematics and atmospheric sciences. This is the expression that we derived in the last video, and it tells us how pressure will decrease with altitude in an atmosphere in which temperature exponentially decreases with height. P is pressure at height z above Earth's surface. P naught and T naught are the values of pressure and temperature at the surface. G is gravitational acceleration, RD is gas constant of dry air, and K, which is important in this video, is the scale factor that dictates the rate of exponential decay of temperature. To refresh your memory from the last video, I'll show you the graph that I presented in last video. Here is pressure and y-axis is height above surface. Thick line represents the behavior of pressure in an atmosphere in which temperature exponentially decreases with height, and the scale factor of exponential decrease of temperature was 1 per kilometer. We can see that if we start with 1000 hectopascals, 1000 millibars at the surface, then pressure at 4 kilometers is practically zero. So pressure really has steep decline with altitude in such an atmosphere. Dotted line is the behavior of pressure in an isothermal atmosphere, and to pretty good approximation it can be used as a pressure decrease with height in our atmosphere of the planet Earth. So you can see the big discrepancy. Now, what we are claiming in this video is the following. If this k goes to zero in the limit case, thick black line should collapse to dotted line. Well, to convince you that this is the case, I have to give you equation for the dotted line, and we know from my previous videos that this equation that describes decrease of pressure in isothermal atmosphere is barometric formula, and P is P naught E to negative GZ over RDT naught. What we need to do now is to let K go to zero, and this expression should become this expression. For K goes to zero, we need to evaluate a limit of this expression. To do that, I will use Taylor series expansion of the function e to power kz around k equals 0. And that would also be known as Maclaurin series. Namely, Taylor series around a point 0 is called Maclaurin series. Anyways, this function e to kz is equal to sum, when sum counter n goes from 0 to infinity, kz to power n over n factorial. Well, what is this equal to? When n is 0, then this is 1, and factorial of 0 is 1 by definition, so we get 1, plus, when n is 1, this is kz, factorial of 1 is 1, so I get kz, plus, when n is 2, I get k squared, z squared, over factorial of 2 is 2, plus, let's do one more, when n is 3, I get k to power 3, z to power 3, over factorial of 3 is 6, 3 times 2. And plus, we write capital O of k to power, this is k to power 4. What this means is the rest here are terms of the power 4 and higher. Now, if we look into this expression, notice that we are interested in the case when k goes to 0. If k goes to 0, this goes to 0. But this term goes to 0 even faster because it's squared. And this one that is cubed goes even faster than this one and much faster than this one. So in this particular problem where k goes to 0, we are really only interested in the first two terms. The reason being, if this one goes to 0, all others go to 0 much faster. Therefore, this expression over here becomes limit when k goes to 0 of p naught e to power g over r d t naught k 1 minus, instead of e to kz, I write this 1 plus kz. And what is this equal to? Well, notice that 1 and minus 1 will cancel, and this minus will go into the bracket, and I will get that this is a limit when k goes to 0, p naught e to g kz, and this minus will go in front, over r d t naught k. But k and k cancels out, and I get that this is equal simply p naught e to the power negative g z over r d t naught. And look, this is exactly equal to this, which proves our hypothesis that this line will collapse to this line when k goes to 0. There is this special excitement and beauty when we connect mathematics with physics, and in this case, atmospheric sciences. There is a mystery in the world of science, and anybody who tries to understand how the universe works in terms of the connection between mathematics and natural sciences. Mathematical tools were initially indeed invented or developed to describe some particular problem. But whoever invented Taylor's series, an exponential function, and limits, I am pretty sure that person didn't think about exponential decrease of temperature with height, how pressure changes with height, and so on. And yet these mathematical tools that were developed, perhaps most likely for completely different reasons, are so effective describing these phenomena in atmospheric sciences. And you can see that across engineering and sciences, physics, that mathematics is extremely useful and effective describing wide range of phenomena. In particular, we think all phenomena in physics and the universe can be described mathematically. Some of them we don't know how to represent mathematically. In some cases, we have mathematical equations, but we don't know how to solve them. The classical example is Navier-Stokes equations that I derive. We can put together a full set of equations, but we don't know how to solve them. So we have to solve under certain assumptions, some special conditions, and so on. That's it for today. Until next video, goodbye.